So I've mentioned that sound travels away from a source and spreads out. Right? So if I have a sound source, let's say, I don't know, like a speaker. Right? Sound is going to leave that source. Let's say it leaves isotropically, which means it leaves equally in all directions. What I drew here was basically a directional speaker, but what I mean is for it to be a source that spreads out evenly in all directions. Alright, so as the sound spreads out, sound that left longer ago is spread out over bigger and bigger surfaces. Alright, and if they are leaving isotropically in 3D, it's spread out over the surface of a sphere, right? So these are actually surfaces of spheres. Now you know when you listen to something from further away, it's quieter. That's because you're receiving a smaller amount of energy from the whole, right? So like if your ear is a certain area, right? Close to the source, you're receiving a greater fraction of the whole, right? What are you receiving? Well, it's whatever the area of your ear is. What fraction of the whole? It's the area of the ear divided by the area of the sphere at that distance, right? The surface area of the sphere at that distance. And this leads us to another idea, which is intensity, right? So there's some power emitted by the source, right? This would be a 40-watt speaker, right? That's a power. And that power is being spread over area. Power per unit area is something that we label intensity. Right? Or given in variables, I equals P over A. Intensity here has units of watts per square meter. Right? And for a wave that's spread out over the surface of a sphere, the surface area of a sphere is pi r squared, right? So it would be some distance r away from the source. Sorry, I said pi r, I meant 4 pi r squared. So if this is spherical, it's power over 4 pi r squared. If we're talking about like a ripple on a pond, that's a 2D surface, so that would be pi r squared. But more generally, we're thinking of things that live in 3D, so it's usually 4 pi r squared. Let's talk about that for a second. What kind of powers do we see for sound? Well, you can hear stuff from pretty far away, right? And you can be pretty close to it, and it can be really loud. You can hear it. It might hurt, but you can hear it. But you can hear that sound from, possibly a mile away. So your ears are very, very sensitive to. Let's not say it that way. Your ears are sensitive to a very, very large range of intensities. Right, your ear is built that way so that you can handle loud noises, but you can also hear very quiet noises. Notice how I got quieter when I said that? That was unintentional. That's just the way. It works. So let's look. There's actually, you can see the range that we're sensitive to. Something like 10 to the minus 12 is the quietest thing you can hear, to 10 is maybe the loudest thing. Maybe 1 is the loudest thing you should really be listening to. Right? But that's a huge range. That's like 12 or 13 orders of magnitude. And so we do something mathematical just to bring that range into something that's easier to manage. All right, and that's this idea of sound intensity level. All right, so intensity is an SI unit of watts per square meter. Sound intensity level is just a way of managing this broad range of intensities. So let me define that, and then we'll come back and do some examples with it. So intensities, so we'll say I ranges from 10 to the minus 12 to, 1, 10, or 100. We'll just say about 10 watts per square meter. Now, that's not entirely true. Sounds can be much quieter than that. Sounds can be much louder than that. But this is the range that that humans are built to hear. All right, so we'd like to bring that range of numbers, this 13 orders of magnitude, back down into something that's more like manageable. So what we do is we take a log base 10 of this. So if you take a log base 10 of an intensity that is something times 10 to the something, you basically pull down the exponent of the 10. All right, so let me tell you this. Let me do it this way. So we take an I, and we often divide by I naught, right? And I naught here is 10 to the minus 12 watts per square meter. And then we multiply this, we set a scale with 10, and we give it units of decibels. Now a decibel is not an SI unit. You can't convert from a decibel to like a meter per something. Does that make sense? It's intensity is the thing that you can relate to meters and kilograms and seconds, but a decibel you can't relate directly to those. It's just a scale that helps us deal with stuff. And again, this is sound intensity level. And it's that word level that is key here. If you just see intensity, that's I. If you see intensity level, that's beta. This is the Greek letter beta. Okay, so what does this do for us? Well, when you plug in I naught, right? So beta at I naught, you're taking a log of I naught divided by I naught, so that's a log of 1, which is 0. So the quietest thing you can hear, so 10 to the minus 12 is the threshold of human hearing. It's the quietest thing that you can hear. Beta is 0. That's great. So beta equals 0 for quiet. Quietest sound that we can hear, right? So this is based for humans. Certainly there are animals that can hear outside of this range, but they're not using the scale, so let's design it for us. And if we go up to, let's say, like 1 watt, so 1 watt, 1 divided by 10 to the minus 12 is going to be 1 divided by 10 to the minus 12 is just 10 to the 12. And you bring down the, well, let's just do it. So beta for I equals 1 watt per square meter equals 10 decibels times log base 10 of 1 watt per square meter divided by 10 to the minus 12 watts per square meter. So what is that? The units go away. I've got 1 over 10 to the minus 12. That's just 10 to the positive 12. But log base 10 of 10 to the 12 is 12. Right? And if you don't believe me, plug it into your calculator. You might have to look hard for the log base 10. We're not using log base E. We're using log base 10. All right, so then that's 12 times 10 decibels. So that's 120 decibels. So beta for the for something that's really loud is 120. And in fact, if we go back to, yeah, this is the best thing I can do. If we go back to the handout, to these tables, you see, like, oh yeah, the threshold of human hearing, beta is going from 0 to like 120 for rock concert, 130 for the threshold of pain. So yeah, like 0 to 100-ish. That's a great scale. Even though the decibel scale is not related to anything SI, it brings this huge range. Okay, so I think you get the point. And decibels is a thing we use very, very often, right, in our everyday lives. Much more often than watts per square meter. So let's do an example or two. So example 3 says, the sound intensity from a jackhammer breaking concrete is 2 watts per square meter at a distance of 2 meters. This is sufficiently loud to cause permanent damage to the hearing of the operator. So let's ask, what is the sound intensity for a person who is 50 meters away? So I'm looking for an intensity, right? You see that? Intensity. Not a level, but an intensity. And then we'll do level in the next one. Okay. So let's draw a picture. We've got a jackhammer. How do you draw? Great. There's my jackhammer. Oh, it's got to have handles. There we go. That's my jackhammer. And it's sending out sound waves. Let's do circles like this. That's great. And we've got 2 distances. We've got one distance that is, call it R1, that is 2 meters, and another distance that is 50 meters. That's R2. So let's write this down. R1 equals 2 meters, R2 equals 50 meters, and what do we have? That I1 is 2 watts per square meter. And the question is, what is I2? Okay, so you might be tempted to take a ratio thing here to say, well, maybe I1 over R1 equals I2 over R2. You can do something like that, but it's not exactly that. So I'm not going to do that for this. I'm gonna solve for the intensity, the power, and then go back and solve for an intensity, and I'll talk about how you could have done it another way in a second. So let's put this up here. So the question is, what is I2? So step 1, I'm going to say, let's solve for power. So remember that, let's say at 2 meters, I1 equals power over R1, 4 pi R1, 4 pi R1 squared. Okay. So I can use the numbers that I have here. So I1 is 2 watts per square meter. Equals power divided by 4 pi 2 meters squared. So you can solve for the power. What you get for that is 100 watts, 100.5 watts. And now I can say, at 50 meters, intensity 2 equals power over 4 pi R2 squared. So that 100 watts is what I'm going to plug in for the power now. So that's 100.5 watts divided by 4 pi times 50 meters squared. And what I get for that is 3.2 milliwatts per square meter. Right? So that's 0.0032 watts per square meter. Or again, 3 milliwatts per square meter. Okay, so that's my answer for the first one. I will point out that they have the power in common, right? So you could have said power equals I1 4 pi R1 squared also equals I2 4 pi R2 squared. So one handy trick here is you see the 4 pi's go away. So I could have said I1 R1 squared equals I2 R2 squared. So you see it's kind of a ratio thing, but you have to square the r's And you have to notice it's I1 over R2 squared equals I2 over R1 squared. So if that's confusing, just solve for the power. That's not wrong. It's just you're solving for a number you didn't necessarily need. Okay, so let's do the second part, which is what is the sound intensity level for a person watching 50 meters away. So now we're looking for a beta. Right, and I want the beta at 50 meters. So it's just 10 decibels times log of I over I naught. So I naught is just a constant, right? That's just 10 to the minus 12. And this equation is just a way to convert from intensity to intensity level, right? It's just a scale change. So we're just going to plug in. The intensity we just found was 0.0032 watts per square meter, and I naught is 10 to the minus 12 watts per square meter. So I will encourage you to be careful when you plug this into your calculator. If you use the E button for the denominator there, it's not 10 E minus 12, that's 1 E minus 12, because the E means 10 to the. So this is actually 1 times 10 to the minus 12. It's just 1 times anything is that thing. So when I say 10 to the minus 12, that's either 1 E minus 12 or 10 caret minus 12. Just be careful. It's easy to be off by a power of 10 here. Okay, so what I get for this is 95 decibels. So it's still pretty loud, right? But it's not. Past the threshold of human hearing. Looks like I lost everything I just did. It's fine. Not a huge deal. So let's do one more example. Yeah, let's do one more example. Let's say, here, your ears are sensitive to differences in pitch, but they're not very sensitive to differences in intensity. That's kind of the trade-off, right? If we can hear a very large range of intensities, maybe we lose some sensitivity in discriminating intensity changes, right? Again, we're pretty good. We're very good with pitch, with frequency changes. Okay. So you're not capable of detecting a difference in sound level intensity of less than 1 decibel. Okay. So I want to know, by what factor does the sound intensity increase if we go from 60 to 61 decibels? Right? By what factor does this increase? So let's write it this way. Beta initial is 60 decibels. Beta final is 61 decibels. Right? So that the increase, right, my delta beta is 1 decibel. I want to know what is the ratio of these intensities, I final to I initial. Okay. So how could we find that? Well, you could solve for I final and I initial, but I don't have a distance to anything here. So there's some math magic we can do here. Delta beta, right, is beta final minus beta initial. That's how I got this delta beta on the left-hand side here. But I could fill in the equation for each of those. That's 10 decibels times log I final over I naught minus 10 decibels log I initial over I naught. So you may remember that when you take a difference of logarithms, it's the same as taking the log of the ratio of the arguments. You may not remember that. That's okay, but it's true nonetheless. All right, so the equation we're going to derive here, we only have to derive it once, right? Once we have it derived, you can use it whenever. So I'm factoring out the 10 decibels. So 10 decibels factors over here, and it's log of the L doesn't look much like an L. log of the ratio I final over I naught divided by I initial over I naught. Okay? So that the I naughts go away here. So that gets me this, that delta beta equals 10 decibels times the log of I final over I initial. Not I naught, but I initial. That's what I'm looking for, is that ratio, I final to I initial. And the only thing I need to plug in is a 1 on the left-hand side, right? Because delta beta equals 1 decibel. Okay, so let's do that. So 1 decibel equals 10 decibels times log of this ratio that I'm looking for. I final over I initial. Okay, so I can divide 10 decibels to the other side. That gets me 1/10 equals 1/10 equals log of I final. Okay, so 1/10, that's 0.1 equals log of I final over I initial. How do I undo a logarithm? Well, you raise each side to that. It's such an awkward thing to say. If I do 10 raised to this, that'll equal 10 raised to this. And 10 raised to the log of this is just the argument. That's like the most awkward thing about logarithms, is that kind of argument. So if that didn't make any sense, don't worry too much about it, because the equation that does that, I'm giving it to you in the equation sheet. All right. So here it is then. It's 10 raised to the 0.1, and what you get is 1.26. There's my 2. Okay. So an increase of 1 decibel is an increase in intensity of 1.26 times. Okay, so we'll play with sound level and sound intensity more in the future.